Today's topic is electrostatic potential. The electric field around a charge can be described in two ways, by electric field, by electrostatic or electric potential. The electric field is a vector quantity while electric potential is a scalar quantity. Both of these are the characteristic properties of any point in a field and are interrelated. Let us discuss electric potential difference. Potential difference between any two points can be defined as the amount of work done in moving a unit positive charge from one point to another against the electrostatic force. To understand it, let us consider a figure shown here. At point O, there is a positive plus Q charge which is known as source charge. Let A and B be the 2 points in its electric field. When a test charge Q0, test charge is always a positive test charge. So when a positive test charge Q0 is moved from A to B, a work WAB has to be done in moving it against the repulsive force exerted by the charge plus Q. We then calculate the potential difference between 2 points A and B by the equation V is equal to VB minus VA is equal to WAB upon Q0. So, the potential difference between 2 points in an electric field may be defined as the amount of work done in moving a unit positive charge from one point to the other against the electrostatic forces. In the above definition, we have assumed that the test charge is so small that it does not disturb the distribution of the source charge. Secondly, we just apply so much external force on the test charge that it just balances the repulsive electric force on it and hence does not produce any acceleration in it. Now, SI unit of potential difference. SI unit of potential difference is volt. So, to define 1 volt, if we put this SI unit of work done, which is joule, 1 joule, and the SI unit of charge, which is coulomb. So 1 volt is equal to 1 joule upon 1 coulomb, and one potential difference of 1 volt can be defined as if 1 joule of work done in moving a positive charge of 1 coulomb from one point to other against the electrostatic forces, then the potential difference between these two points is known as 1 volt. Now, electric potential. The electric potential at a point located far away from a charge is taken to be 0. If point A lies at infinity, then VA is equal to 0, so that V is equal to VB is equal to W upon Q0. So, the electric potential at a point in an electric field is the amount of work done in moving a unit positive charge from infinity to that point against the electrostatic forces. SI unit of electric potential is again volt. The electric potential is said to be 1 volt if 1 joule of work has to be done in moving a positive charge of 1 coulomb from infinity to that point against the electrostatic forces. Here, the point to be noted that the unit of electric potential difference or unit of electric potential both is same. The difference in defining 1 volt of electric potential difference or 1 volt of electric potential is only hidden in their definition. That means if we want to define potential difference of 1 volt, then work is to be done in moving a positive charge from one point to another. And when we define electric potential of 1 volt, then work has to be done in moving a positive charge from infinity to that point. Now let us calculate electric potential at a point due to a point charge. Now let us consider that Q be a positive charge at origin O. Now we want to find its electric potential at a point P, which is at a distance r from it. So in the figure it is clear that the point charge P is located at point O, and P is the point at which we want to find the electric potential due to this point charge plus Q. Now by definition, the electric potential at point P will be equal to the amount of work done in bringing a unit positive charge from infinity to the point P. So suppose a test charge Q0 is placed at a point A at distance x from O. By Coulomb's law, the electrostatic force acting on charge Q0 is given by the expression F is equal to 1 upon 4 pi epsilon naught Q0 upon x square, and direction of this force is away from the charge O, away from the charge located at point O, that is the direction is from O to A. Now the small work done in moving the test charge Q0 from A to B through a small distance dx against the electrostatic force will be dW is equal to F dot dx. Here the F and dx both are in opposite direction. Force F is from O to A, that is away the positive charge, and we have displaced Q0 from A to B, that is opposite to O to A. So the angle between F and dx will be 180 degree. Now we know that the scalar product A dot B is equal to AB cos theta. So here F dot dx can be written as F dx cos 180 degree. Cos 180 degree is minus 1. So dW is equal to minus F dx. This is a small work done. Now we want to find the work done when the charge Q0 is brought from infinity to point P. So we have to integrate this small work done. So W total work done, W is equal to integration of dW is equal to integration from infinity to R minus F dx. Putting the value of F, 1 upon 4 pi epsilon naught Q0 upon x square dx. Now when we integrate, the constant terms comes outside. So 1 upon 4 pi epsilon naught Q0 being constant comes outside from the integration sign, and only inside the integration side x square remains. Now just recall the formula of integration. Integration of x raised to power n dx is equal to x raised to power n plus 1 upon n plus 1. So by using this formula, integration of x raised to power minus 2 becomes minus 1 upon x, and the limits are infinity to r. So W is equal to minus 1 upon 4 pi epsilon naught Q0 in bracket minus 1 upon r plus 1 upon infinity. 1 upon infinity being equal, only terms remaining terms are W is equal to 1 upon 4 pi epsilon naught Q0 upon r. So from here we can calculate W upon Q0, which is equal to 1 upon 4 pi epsilon naught Q upon R. And as by definition, we know that W upon Q0 is the electric potential. So electric potential at point P due to the positive charge plus Q will be given by V is equal to 1 upon 4 pi epsilon naught Q upon R. So this is our formula for the potential at any point due to any charge. So V is equal to 1 upon 4 pi epsilon naught Q upon R. Now here we have to keep in mind that vector that potential V is a scalar quantity. So in numericals, whenever we have to find the value of V, we will put the value of charge Q with sign. Means if the charge in the question is positive, we put plus Q, and if the charge is negative, so we will put the value of minus Q with negative sign. So V is equal to 1 upon 4 pi epsilon naught Q upon R. It also tells us that V is inversely proportional to inversely proportional to R, and the graph between potential and distance will be like as shown in the figure. Thank you.